present my work here. This work is joint work with Tarzia. First, it concerns one example. I present an example of free boundary. It's a heat equation. U is the temperature, and in the domain, omega is a bounded domain with the boundary is composed of 3 parts, gamma 1, gamma 2, and gamma 3. On gamma 1, we put the Dirichlet condition. I think, no. Yeah, it's a blue condition. And we have in gamma 3 Neumann condition. And in gamma 2, we have a Tresca condition. It's a friction condition with Q is given and K is a constant. If Q is the flow is in the first case, U is equal to 0, and in the second case, we have friction of the temperature. We have also the initial condition and the compatibility condition in the last. If we choose the constant H positive, and if we change the Dirichlet condition by the Newton condition, which is here, we obtain another family of problems. And then we want to study the case when the constant H go to the infinity. Here, if we divide by H the Newman condition, the Newton condition, and we pass to the limit, we obtain the Dirichlet condition. We want to do this rigorously and to study the main point here. I will present boundary optimal control problem of these two problems, or this family of problems, or problem which generalize this problem. Then I study the existence and uniqueness of this optimal problem. Then we study the convergence when the parameter H go to the infinity. We study the limit of the optimal control and the state associated. Okay, the optimal problem is, the first one is this one. For the constant m positive, we look the problem P is the the optimal, the minimization problem, where the functional G, the co-functional, is defined here, and UF is solution of the variational problem, VI. The functional phi come from the Tresca condition. For this problem, we can have existence and uniqueness. It's an old situation. We can obtain also for a given H positive and the constant M and B, the problem PH, which depend on H, and we have also the cost functional GH, which depend on the solution UHF, which is the unique solution of the variational problem, which is here. The difference of the two variational problems that here the bilinear form depend on the older linear form, and we can consider here all situation until the bilinear form must be coercive continuous, not only the two problems I defined before. And also, if this one is coercive and continuous, we can prove that this one also is coercive and continuous, and then we obtain also existence and uniqueness of this variational problem. So now to prove the existence of the optimal problem, we have this theorem. And the idea to prove this theorem is to prove that the cost functional are strictly convex. How to prove this? To prove this, we define the convex mu is in 0, 1, and we consider the convex combination of the F1 and F2 and UF1 and UF2, which are two solutions of the variational problem with F1 and F2, and the difference of U3 and U4. U3 is the convex combination of two solutions, but U4 is the solution of the variational problem with F equal to F3 is the difference. Then we look to prove that the cost functional G is strictly convex, and we obtain this result. The red bar must be positive. How to prove this is positive? We must prove this part. The first part, this one, is easy to obtain using the weak maximal principle. But the other part, we must, here is the same for the other problem with H. Then with the weak maximum problem, we obtain the positivity of the two solutions. Same. And here we want to prove that U4 is smaller than U3 for all mu in 0, 1. Then to prove this, the difficulty is come from the Tresca functional phi. And so we approximate this functional by phi epsilon, which is Gatto differential. Then we consider an approximation of the variational problem, and we try to prove this inequality. With this inequality, it's technical, we obtain for all epsilon that U4 mu is smaller than U3 epsilon. And then we must prove that we have the strong conversion when epsilon tends to 0 to obtain the result. With this we obtain that the cost functional are strictly convex, and then we obtain the uniqueness of the optimal convex. Now to pass to the limit. To pass to the limit, we must prepare some conversions before to obtain the last theorem. And the first convergence is this one we must prove that U hash f, the solution of the variational problem V hash f, converge to the solution of the other problem. This is come from manipulation of the variational problem. We obtain this and we take the bilinear form HF like this. So from this we obtain this convergence. This is interesting. So we prove that the derivative converge to the derivative of mu, and we want to identify eta that is UF. Then this one, prove the, and from this we can pass to the limit to obtain this one. And when we obtain this one, we use the uniqueness of the solution to this variational problem. Then we find that eta is equal to the solution UF. Okay, now we have weak convergence of UHF to UF, and we want the strong convergence. Then we take phi h is equal to UHF minus UF, and with this we can pass to the limit in the second part using the weak limit, and we have 0, we obtain the result. Now we want to prove the main theorem. It's this one, that the convergence of the state dependent on h to the state not dependent on h, and also of the control dependent on h and the control not dependent on h. And to prove this result, we use, if we prove this, we have this corollary, it's automatically. Okay. Then to prove this result, we begin with,
the computer went idle. If you scroll it on the computer, it should
Just
move
push
the mouse.
somewhat.
Or
yes, here I see, but here's not, yeah, there is no.
it is.
Ah, here. First, we prepare also some conversions. The first convergence, we want to prove that f opt h converge weakly first. Then we prove that it converge strongly. First, it converge weakly. And here we obtain this result from the cost functional. The cost functional g h of h is by definition equal to this part. And as this we obtain this part, then we can choose f equal to 0. When we choose f equal to 0, we obtain this inequality. And to obtain this result, we must estimate this part. So this one is solution to the variational inequality, this one. And so from this we can obtain the estimate of U0 average. So have this part. Now we can obtain this convergence. The first one, it's in U1, because before we obtain not in V. V is V is L2. And we want to prove this one and to prove the convergence for on the boundary. So for this we consider the variational problem, and with this variational problem we use AH. We can rewrite AH like this. Then we have this part, and we can pass to the limit in the second part, and we obtain this result. Now we want to obtain the convergence 6, and to obtain the convergence 6 we might we must just write this inequality, and then we obtain the first one. The convergence on the boundary, how to prove it? The condition on the boundary, we must have 6 and we must have 7. And then we use the open compactness argument with the 3 spaces to obtain the strong convergence in L2 0T, this space. Then we use the continuous injection of this part to obtain this one, 4. Okay, we have this. Now we want to identify the eta that is equal to the solution of the variation. So we choose the test functional, and we obtain this result. As the blue part is positive, we can delete it to obtain this one, and from this one we can pass to the limit, and when we pass to the limit we obtain another time this inequality with the uniqueness of the variational problem. Eta must be equal to U. Okay, now we must obtain also that F tilde equal to the optimal of F. So we write this GF tilde, and then we can use the strong convergence in the lemma 1 to pass to the limit to obtain this one. And this one is this. So we have this for all F. So F tilde is the optimum, and the optimum is unique. Then we obtain this result. Okay. Now we want to prove the strong convergence. How to prove the strong convergence? We consider the variational problem with the test function. We obtain this inequality, and we use all the convergence we obtain. For example, for that U hash often hash converge weakly in eta, then we can pass to the limit, for example, here. And from this, we can pass to the limit here. And from this, we can pass to the limit here also using this one. Then we can pass to the limit here to obtain this result. With this, as we have obtained eta is equal to u f tilde, and f tilde is equal to f opt, we obtain so the first result of the theorem. Then we want to obtain the convergence of the control. So we obtain first this from 10. No, from this. We obtain this g f tilde is smaller than this one. So we obtain this inequality. The first is by definition. The second one using also the definition of limit m. And then we obtain that this one is equal to this one. So as this converge to this one, we obtain that this one converge to this. Okay? We obtain this result. With this result, now we write the 12, and we use in the last part the weak convergence of f opt h. So the second part go to 0, and we obtain the second result for the. With this, I finished before that.